the extension 2 will end up looking at a whole heap of different techniques to integrate, things to look for to help us do it. This is probably one of the simplest ideas to search for first of all. If you can set it up in such a way that you've got the derivative outside the function to the power of n, then you know that it must have come from that function to the power of n plus 1. Because you would have used the chain rule to differentiate. You would have brought down the power, lower the power, and then the derivative of the inside would be there. So it's sort of like going backwards. So if we do see that pattern where you have got some function to a power, but the derivative of that function is multiplied by it, then we know, just like with polynomials, we could just add 1 to the power over the power to that function. Now, sometimes they set it up by getting you to differentiate something first and then go, oh, hence integrate this. So it sort of gives you a bit of a clue. So they might say something like, oh, well, go and differentiate the square root of 1 minus x cubed, which of course we would use the chain rule for. We'd bring down the power, lower the power, put the boot in. There's the minus 3x squared, and you get minus 3x squared on 2 root 1 minus x cubed. And then they go, oh, hence go and find this integral. And you'll notice the similarity between the two. The only difference is, this one is just x squared on 1 minus x cubed. The one before had minus 3 on 2. But constants are fine, because we can always factorize constants outside of integrals. So if we set it up so that we've got what we just differentiated, and that's the minus 3x squared on the 2 root 1 minus x cubed. But of course, we can't just change the question. So we balance it out by multiplying by a constant, and we put that at the front of the integral, of minus 2/3. And then we can use the logic that says, well, hang on a sec, if I just differentiated the square root of 1 minus x cubed and got minus 3x squared on 2 root 1 minus x cubed, then logically, if I integrate minus 3x squared on 2 root 1 minus x cubed, I must go back to root 1 minus x cubed. So that'll just be minus 2/3 root 1 minus x cubed. So that's when they set the question up for us. It sort of like makes it a little bit obvious. You go, of course. But they don't always set it up, and that's where we're going to look for that pattern. Can we make this the derivative times the function of some power? So we've got x times the square root of 2 plus x squared. Well, it's almost there. I mean, the derivative of 2 plus x squared is, of course, 2x. We've got 1x. Constants are not a problem. We can always multiply by that constant and then divide it as well. So if I multiply by the 2x and divide it by a half out the front, I can say, look, my integral now, I've got the derivative times some function to the power of n. So I can just add 1 to the power over the power. So 3 on 2 divided by the 3 on 2. And there's our answer. A bit of work to be done, of course. Half times 2/3 would be 1/3. And of course, a mere mortal would leave it in index form, but we'll put it in as 2 plus x squared root 2 plus x squared. Another technique that we'll see later on is an idea that's called integration by substitution, where you change the function into something easier. And so the thing that's giving us difficulty here, I guess, is that function. And so you say, all right, well, let the function be just some other pronumeral. We'll let u equal 2 plus x squared, and we'll change our integral. So everywhere I see 2 plus x squared, I'll replace it with u. So it'll replace all the x's, though. I also have to replace the dx, because I'll end up integrating with respect to u rather than with respect to x. So how do I work out what dx is? Well, my substitution over there is u equals 2 plus x squared. So du dx would be 2x. So I could substitute du for 2x dx. Normally when we're doing this substitution, by the way, we don't worry about this middle step. We just automatically go, du is 2x dx. Okay, so how can I substitute everything in? Well, 2 plus x squared, that's what we said was going to be u. The other thing we need to get rid of is the x dx. Well, du was 2x dx, so actually I've got a half of du there. And so I could turn that into a half, u to the half, add 1 to the power over the power. Now, of course, if that's in terms of u, That's a pronumeral I introduced. The original question had x's, so I go and put the 2 plus x squared in for u. It's okay, but if you spot the pattern, it's quicker. Like you spot the pattern and say, hey, all I need to do is create the derivative. It's going to be a lot quicker than mucking about with substitution. I mean, substitution is useful, certainly for some more complicated functions. But if you spot the pattern, take advantage of the pattern. Okay, so let's have a look at this one. X squared on x cubed minus 2 cubed. And I notice that x squared's on the top, and on the bottom I've got an expression involving x cubed. So when you see polynomials, if you see something like that where the power of one polynomial is 1 less than the other power, then there's a good chance you could create a derivative here. So I'd actually like 3x squared on the top. So I can balance that out with a third, and then I end up with 3x squared, and there's my function, x cubed minus 2 to the power of negative 3. So I've got it in that form, derivative times the function to some power. So I can add 1 to the power over the power, substitute in 1, substitute in 0, but you'll notice again, when I substituted in, I took it out of index form because it just gives a nice cleaner solution, and we end up with minus 1/8. I mean, I suppose 1/8 is something you're going to get an exact value on the calculator for anyway, so it probably didn't matter. But I mean, you can't always guarantee it's going to be a nice exact decimal. If I did this one by substitution, then I would say, okay, well, my function that's causing me a problem there is the x cubed minus 2. So all right, du then would be 3x squared dx. So I could change this integral, but there's another problem with doing integration by substitution. Those limits of 0 and 1, they refer to x. My new integral is going to refer to u, so I need to change those as well. How do we do it? Well, the same substitution. U is x cubed minus 2. So when x is 0, u would be negative 2, so that'll become the new lower limit. When x is 1, u would become negative 1, that'll become the new upper limit. So I could change it to a third, u to the minus 3, minus 2 to minus 1. I suppose this would now is where substitution can actually be quicker, because all I've got to integrate is u to the minus 2, and you'll notice it's the same numbers I'm substituting in, minus 1, minus 2, but I'm substituting straight in. I didn't have to do a calculation. The substitution has already done the calculation for me. And obviously we get the same answer. Again, still I probably personally prefer to spot the pattern and just go straight into it. One of the unfortunate, well, I'll say unfortunate, thing about an Extension 1 exam is often they give you the substitution, they force your hand, and you sort of look at it and go, what are you getting me to do that for? It's so obvious, all I've got to do is this. But if they tell you to do it by substitution, you've got no choice. I suppose really because they're not testing to see whether you see the pattern, they want to see whether you know how to do integration by substitution. That's it. More on integration by substitution later. So for now we'll just look at 11H. I encourage you to look for the pattern rather than go with the substitution idea on those. So you can find that pattern of derivative times some function to the power of n.